Okay, this is the chapter 17 video problem. So original function is fxy equals 4x to the 0.75 power times y to the 0.25 power. There's a total of $12.8 million available for labor and capital, and the firm's costs are $800 per unit of labor and $1,600 per unit of capital. So our equation is going to be 800x plus 1,600y equals the 12,800,000. And then to make that into our constraint, we do 800x plus 1,600y minus the 12.8 million equals 0. So that's the new constraint. And then to do our Lagrange function, we do the original function, which is 4x to the 0.75 power times y to the 0.25 power minus Lagrange times the new constraint, which is 800x plus 1,600y minus 12.8 million equals 0. And then you have to multiply that out, which is still the original function, minus an 800 Lagrange x minus a 1,600 Lagrange y plus a 12.8 million Lagrange. So that's our new function. And then we take the partial derivatives f of x first, which is going to be a 3x to the negative 0.25 times y to the positive 0.25 minus 800 Lagrange. And then f of y partial derivative is a 1x to the positive 0.75 times y to the negative 0.75 minus a 1,600 Lagrange, and then f Lagrange partial derivative would be a negative 800x minus a 1,600y plus the 12.8 million. So then you have to set the partial derivatives equal to 0 and then solve for the systems of equations. So our first one is going to be f of x, so that's 3x to the negative 0.25 y to the positive 0.25 minus 800 Lagrange equals 0. And that is going to turn into a fraction, so that's going to be Lagrange equals a 3y to the 0.25 power over an 800x to the 0.25. And then f of y is going to be a 1x 0.75 y minus a 1x to the positive 0.75 times a y to a negative 0.75 minus a 1,600 Lagrange equals 0. And that's also going to turn into a fraction, but that fraction is going to be 1x to the 0.75 power over a 1,600 y to the positive 0.75. And then you take those two fractions and set them equal to each other. So we will have a 3y 0.25 over an 800x 0.25 equals a 1x 0.75 over a 1,600y 0.75. And then we are going to cross multiply, so that leaves us with a 4,800 over 800, which comes out to x equals 6y. And then we're going to sub the 6y into the partial derivative of f of Lagrange. So that's going to be a negative 800 times a 6y minus a 1,600y plus the 12.8 million and it all needs to equal to 0. So we're going to multiply the negative 800 times 6, which gives us the negative 4,800. Then we're going to subtract or do minus 1,600, which gives us a negative 6,400. And then we're going to do that negative 6,400 y is equal to a negative 12.8 million. And then we're going to divide the negative 12.8 million divided by the negative 6,400, which gives us y equals a 2,000. And then we're going to plug that 2,000 into our x, which was 6y, and 2,000 times 6 equals a 12,000, so that is our x. So our 2 points are x is 12,000 and y is 2,000. So our answer is going to be the function fxy equals 4x to the 0.75 times y to the 0.25 has a maximum point at 12,000, 2,000. Production will be maximized when 12,000 units of labor and 2,000 units of capital are used. So in order to find how many ropes that are going to be produced, we're going to plug our x and our y into the original function. So we have 4 times 12,000 to the 0.75 power times 2,000 to the 0.25 power, and that comes out to 30,669.269. We're going to round that to 30,669 160 meter ropes that will be produced.